Yeah, I guess you can start right.
Yes, sir.
Um, it's Castro here. Castro is not yet in. Ibrahim
No,
is
sir,
also
it's not
here.
yet.
Mr. George. Yes, I think Mr. George is here. Mr. Francis is also here. Okay. I guess today is the last week for the course, right?
Yes, please.
Yes,
Okay.
please. Yes.
Um, so with the unit 4, as we do always, I'll be doing the session 1 to 5 with you. Then you do the session 6. The session 1 is the introduction to elementary particles. We talk about quarks, leptons, fermions, and bosons, hadrons, and forces at a fundamental level. So basically, this is talking about the basic makeup of an atom. We said atom, the smallest particle is what? The smallest particle of every particle is the atom, right? Even the atoms, we have the smallest particle that make up those things, and those are the um, leptons, fermions, and bosons. So that's what we are going to do. The type of forces that exist between those basic level. Yeah. But then before we start, sorry, last week the session says, what did you guys learn over there? Was there any um, problem? Was there any misunderstanding or anything? Hmm? Hello.
Hello, sir.
The one we did last, the session says for unit 3, was there any misunderstanding there?
For me, no, sir.
Okay. Since no one is saying, it's not talking, means it was okay for you guys.
Yes, sir.
All right. And I don't bring questions and admin sessions and be telling you nothing before you can do it. Since no one is saying you didn't find it difficulty. All right. So, okay, so we start with the brief modern particle physics, of which we've done.
Sitting at the backyard, you should always be at the front desk. But I'm teaching you to turn. Kofi na akɔ egya wo. Ɛsɛ.
Yes. So the brief history, I know you've done part of it when you were doing the modern and atomic physics. You did a little bit of the history, so I won't waste my time here. So with the modern physics, it began in the early 20th century as the exploration into the structure of the atom, right? And the discovery of atomic nucleus in the Goldford experiment of Gigamassin and the Rutherford was the foundation of the field for that of the atomic physics. The components of the nucleus were subsequently discovered in 1919. That's the proton. And in 1932, the neutron was also discovered. In the 1920s, the field of quantum physics was developed to explain the structure of the atom. I think with this, you've done that before, so where should we start? So, with the basic or with those things established, that's all of them coming up with the protons and neutrons, which are the basic fundamentals of atoms. There were questions that was raised. The question were, are protons and neutrons the fundamental, like that's the basic particles of an atom? And that's the question that was arised, because we all know that he said every particle, the basic or the simplest is the atom, and the atom is also consistent of the protons, neutrons, and electrons. And so if the basic or the smallest particle that we can find, the smallest component can find in an atom, a particle is the atom. We are saying the protons, neutrons are also the smallest particles within it. That means that's supposed to be the smallest. But then that wasn't the case, which means even with that are the smallest, there's something that comes to make up the whole thing. Okay. For example, we are saying so you are saying in the beginning there was this, there was that, right? For example, as an example here, okay. So we said God created heaven and earth. That's in the beginning. That was the first thing that was created, right? And now some people are also going about saying, is that the first thing that was created? And that becomes a question mark. The same thing applies here. You are saying the basic thing that exists in the, or the fundamental thing that exists in every particle is the atom. And in the atom, the things that comprise or the things that make up the atom is the protons, neutrons, and the electrons. But then we did extra analysis or extra experiments was it, and we realized even though that was what they were saying, but then that wasn't the basic. And that was what leads to the exploration of the quark leptons, mesons, and bosons. Okay. Now, to escape the particles, the next logical step was to investigate whether these particles could be explained by postulating that all baryons and mesons are made up of other particles. Okay. And I know we've talked about the baryons and the mesons. That's when we were talking about the matter and antimatter. I remember we mentioned that. And these particles were named quarks. So if you take the baryons and the mesons, right, they were named as quarks. So if you take quarks is just a name given to the combination of baryons and mesons, right? And within these baryons and mesons, we can have subdivisions. Okay. As far as we know, quarks are like points in geometry. So quarks are like points in geometry, as we did. So the Cartesian and those things, when you see quarks, then we are talking about some points within a specific plane or something. Okay. They are not made up of anything else, meaning they are not also made up of anything, meaning this can be the fundamental, the basics. The basics. After extensively testing this theory, scientists now suspect that quark and the electron, and a few other things we will see later are the fundamental. So basically, the quarks and the electrons are the fundamental, meaning the protons and neutrons are made up of barons and mesons, which are also known as the quarks. Okay, so in the nucleus, that we say the only thing that exists is the protons and neutrons. What made up those protons and neutrons are the quarks. Okay. Now, the other question that arrived was, what are then elementary particles? What are the elementary particles? Because you've now gotten to know that the protons and neutrons are not the elementary ones. So, what are those elementary ones? Now, we have to explore what elementary particles are. An elementary particle or fundamental particle is a particle not known to have a structure, right? That is, it is not known to be made up of smaller particles. It's not made up of any smaller particles. So it means that the smallest. Okay. If an elementary particle truly has no substructure, then it is one of the basic particles of the universe from which all larger particles are made. And yes, that is true, because if we have the elementary or the smallest particle, it's the smallest particle that builds up to get a bigger one. Hope you understand that.
Yes, sir.
Okay. On the other hand, there are composite particles. That's particles having an inner structure which consists out of two or more of the elementary particles. So if you talk about the composite particles, these are the structures or the inner structures that consist of more of the elementary particles. So it could be the quarks. Okay, so the composite particle consists of quarks, which are the mesons and mesons. Okay. Nucleons are an example of this. Of course, composite objects can consist out of composite objects like nuclei, atoms, or molecules. Such composite objects are called bond states. In the course of history, many instances are known that particles previously recognized to be elementary have actually been composite. So, what we first termed them as the elementary particles were not elementary particles, but what? Composite, which means they were made up of more of the elementary particles. So we can talk of the protons and the neutrons as well, because those was what we thought was the elementary particles as far as atomic physics is concerned. But then further studies realized that those were not the elementary particles, meaning it is also made up of some other particles, and those particles that are made up of what we are talking about right now, which are the quarks, right? And so then protons and neutrons are said to be composite elements because they are made up of these elementary ones, such as the quarks. Okay. Today, nobody would be too surprised if any of the elementary particles known would, in fact, be composite. Yes, so as we are saying, the elementary one that we all know, now it wouldn't be surprising to say they are not the elementary, but rather they are composite. So, for as far as we know, we have some of the things that we think their basics or the simplest is this. It's because maybe there have not been any further studies done. Meaning, if further studies is done and we're able to find out that those are not the elementary, then we can say then those that we thought it was elementary is now a composite instead of the elementary. Okay. Through a long series of experiments and theoretical studies, that there existed a very simple scheme of two basic sets of particles, that are the quarks and the leptons. Okay, the quarks and the leptons. Among the leptons are electrons and neutrinos, and a set of elementary forces that allow these to interact with each other. So the quarks are basically what make up the protons and neutrons, but the leptons are the ones that comes to make the electrons and then the neutrinos. And neutrinos are kind of anti-electrons. Okay. By the way, these forces themselves can be regarded as being transmitted through the exchange of particles called gauge bosons. An example of this is the photon, the quantum of light and the transmitter of electromagnetic force we experience every day. Okay. Then move on to the scale of the atom. While an atom is tiny, the nucleus in 10,000 times smaller than the atom, and the quarks and electrons are at least 10,000 times smaller than that. So as you are saying, the smallest particle of an atom is the protons and the neutrons. He said most of the quarks and the electrons are less 10,000 smaller than what we thought. If you talk about these quarks, they are very, very, very small, very, very, very small. Okay. We don't know exactly how small quarks and electrons are. They are definitely smaller than 10 to the power exponent negative 18 meters. And they might literally be points, but we don't know yet. So those quarks and electrons, we have no definite size for them, but estimation is almost around 10 to the power negative 18. But then we are also saying because of their particle size, they are assumed to be points. They are assumed to be points, but as it stands, we don't know. And we are assuming it's point because if we have a very tiny size like that, it's hardly would you see it undergoing any motion. I don't know if you can see that picture. For example, rotation of the Earth around, or rotation of the Earth on its axis. When we are on Earth, or when we, yes, as we are sitting or we are living now, we do not see the Earth moving, right? But then, if you take it to the, you take that kind of speed that the Earth is rotating to the smallest particle to see or observe how it's rotating, you realize it's undergoing a very high motion. Why? Because the mass of which the Earth is bigger as compared to that of the tiny particle. Okay, and hence the momentum to move the Earth is very, very high, or very, very much greater as compared to that of the smallest particle. Hence, if you are comparing those two, one will be observed very high as compared to the other one. Likewise, when you are talking about the elementary particles, they are very, very, very tiny, right? To the extent that if they are undergoing motion, it's hardly for you to see. And hence we are saying they are seen, or they are literally like a point instead of a moving object. I hope you understand it.
Yes, sir.
Okay, so in this case, in order for us to see their movement, that's where the composite comes in. Okay, because we said composite made up of many of these quarks and leptons. So if they come out to be a big enough, and hence we can see the movement. For example, if one person is trying to push a car and the car is not moving, it's not that the person is not pushing, just that the force the person is applying is not as much that can be used to move the vehicle or whatever it is. But then if you get 10 times of that same force applied to that object or whatever you are applying to, you see some kind of changes, which means that the summation of the individual ones is what is able for us to observe the movement or the motion. So with the single particles, it's literally seen as a point, but when it forms a composite, now each of them is coming together to add their momentum and everything. So in that case, you can see their movement, and hence that will not be seen as a point, as is seen as a individual particle. Okay. It is also possible that quarks and electrons are not fundamental after all, and will turn out to be made up of other more fundamental particles. So as it stands now, it could also be observed, or it could also be further proved that since we're able to say neutrons and protons are not the fundamental, but rather the fundamentals are the quarks and the leptons, which we see them as a point like. It means you could also go further and find out is the leptons and quarks the basics, but as it stands, there has not been any further studies done on it. And I think why they've not done that is because even the leptons and the quarks, they are seen like a point, right? Literally like a point. So if I'm seeing it as a point, what then again can I go further to do? Because we are expecting them to be in motion, but what I'm seeing is not in motion. So what else can I further to find? And I think that's why we've not done any further studies. Okay. Now let's look at the size. So if you take the size of a proton and neutron, this is that. This is the size of a proton, this is the size of the electron, right? And this is the leptons and the quarks, the size. So if you compare them, the protons, the size of, if you take the atom and you take the proton and neutron, and this is the proton alone, and this is the electron, you take the size of a quark, you see the quark is almost a ratio of 100 million as that of an atom. And quark is 100,000, a ratio of 1 over 100,000 to that of a proton. And to that of the nucleus, that's a combination of the proton and neutrons, is approximately 1 over 10,000. So you can see the size as compared to each of them. That's if you take the elementary one compared to the atom that we say is the smallest particle. And that's why we are almost seeing them as a point-like objects. Okay. Please, any questions so far? Okay. So we want to spin that as a property of a particle. I think you've done that in quantum mechanics now. The spin and angular momentum.
Yeah, I think someone has raised up his hand.
Okay.
Yes,
Yes, Mr. Francis, go ahead.
they said the quarks and the electrons are at least 10,000 times smaller than the.
Please hold on. Yeah, go ahead, please.
They said they are smaller than 10 to the power negative 18, the electrons and the quarks.
Please come again.
Hello.
Yes.
They said the electrons and the quarks are smaller than 10,000 raised to the power 18, negative 18.
Uh-huh.
But in the diagram here, the comparison, they are saying it is 10 to the power negative 18.
Yes, in the diagram here, they are not being specific. They are giving a ratio, as in the total, like a raw estimation.
Okay.
Yeah. Any other question? Hey. Still, Mr. Castro is not in. Mr. Ibrahim is not in. Madam Fisher is also not in.
Please,
Sir, please, I've joined. I'm here.
I'm in.
Yeah, I'm in.
I'm in.
So let's go on.
So,
I was.
I overslept. I had to do something late at night, so I overslept. I slept around 3 o'clock.
Okay. Say no, Friday, PD.
Don't pay you, please. Let me code. I was coding.
Coding in what? What language?
Oh, Python. I was using Python. I'm making some project B.
Oh, okay. I thought MATLAB or any other than Python is fine.
No.
Okay. So I was asking, I hope the spin have been taught in quantum physics. So professors have done that with you guys, right?
Yes, I think so. The spin
Oh.
and the
Please throw a little light on it.
I should throw like please.
All right.
Who said I should do light? Mr. George.
Meaning it wasn't that clear. I told you that the exams, when you write now, we forget. So we learn for that exam. It is gone. So this one too.
No. Quantum physics of which you are doing now. No, which exam do you write and you forget about it?
No, I said the spin. When we learn it,
That's what I'm saying.
It's gone.
Quantum physics, you have to do it in quantum physics. So which exams are you talking about?
You've not done it in quantum physics. I'm not yet there.
Hey, we have done it
Okay,
to.
they think that we have not done it.
We have done it, please.
We see now.
Say I no pay and did you. I'm going for the day and Jabba for margin.
You have done it. The spin and this thing, you have done it. You have done it in quantum physics.
Mr. George. Mr. George, Mr. Francis, not just say, oh, okay. Vem.
We learn
There
it in
was
a different subject. Let's learn it. Let's
Throw
learn it
more
in
light
this.
on it. I'll lend you my torch. Throw more light on it.
No, it's for the dorsal.
So spin, that's the property of a particle. Now, spin is a value of angular momentum assigned to all particles. So if you take any particle, we have a spin, okay, whether it's up, down, a half integer or something in that order, right? So if you take any object, whether electron, proton, or whatever, they have their own spin number. But then, as we said, if you take proton and electrons, those are not the fundamental. Meaning, if you take the electrons and the quarks, they also have their spin, and the spin tells you the position or let me see the position of the particle we are talking about. Okay. When a thought spins, it has a certain amount of angular momentum. So when you are talking about a spin, you also have a certain angular momentum. And the momentum, as you know from momentum, that one day I know you know. And if you talk about angular momentum, too, you know. Right. Mr. Castro, angular momentum here then. Not in quantum physics, today in general physics. If you say angular momentum, what comes in mind?
Hello, sir. Can I talk?
Yes, you can talk.
I'm talking about the speed needed for the atom to spin across the orbit of the speed needed by the electron to spin across the shells of the atom. That's my knowledge.
Yes, that is it. So if you talk about angular momentum, basically we say the electrons are at the shells of the atom, and those shells are what? A spherical shape. They are circles. So if you are talking about angular momentum, the speed or the momentum needed for it to orbit around that circle, that's what the angular momentum is talking about. So if you take any angular momentum, it has a spin. Okay. This idea of angular momentum is also applied to particles, but it appeared to be an intrinsic and changeable. Any question? It's appeared to be an intrinsic and unchangeable property. For example, an electron has and will always have a half of spin. That's if you take the spin of an electron, it always have. In quantum theories, angular momentum is measured in units of each bar. That's the reduced Planck's constants. So if you are talking about angular momentum,
About the spin.
okay.
So I want to ask a question about the spin.
Okay.
The spin, is it a property that is specific to a particular particle? Because if you said all of them have got their own spin, then why is one having half of it? If you say one is having half spin, then it means that there is a spin, and then this one there's a general value for the spin, and this one have got half of it.
Yes, if you talk about a spin, every particle has an assigned spin number. Okay, every elementary particle. Okay, so if you take a composite function, a composite particle, you can find the spin of that composite particle. How? Assuming we are saying a particle is made up of, let's say, 3 electrons, right? And the 3 electrons, each of the electron is having a spin number of half. So what would be the spin for that composite function or the composite particle? Okay, so if there is a matter of just adding a spin, so those are the things they use in calculating the spin. And it has been done and kind of be a standard thing. Okay, so it's a standard thing that it has been assigned to any particle, and it's not that it's standard because it was chanted and it came from the sky. No, it was computed. So after computing, they got to know, okay, when you take this particle, there's this spin number. If you take this spin number, based on the composite function within that particle. Is that correct, Mr. George?
Yes, sir. Thank you.
Okay. So as we said, for the spin, all we know is it's either half, as I said, it's a half integer, right? But then when you are dealing with quantum theories, angular momentum is also measured in a unit of h bar, right, which is joule second. With that one too, as we are talking about the spin and the angular momentum, they also have their own characteristics or properties. Okay. And h bar is nothing serious or nothing new by nothing new but just the normal Planck's constant divided by 2 pi. So if you hear reduce Planck's constant or quantize Planck's constant, we are talking about the h bar, which is not anything you have not seen before, but then it's just the normal Planck constant that you know, that's the h divided by 2 pi, and that's the h bar. And that's the unit for the, I'm sorry, yeah, the unit for the angular momentum. Okay. Then go to classification of particles according to spin. So now how do we classify particles based on their spin number? So elementary particles can be classified according to their spin. And these spins includes, if you talk about fermions, fermions are having a spin number of half, bosons are having a spin number of 1, and scalar particles have a spin of 0. Okay. And these are some of the things that come up to make some of the spin for other particles. Okay, so for example, as I said, assuming if we are saying protons is made up of, let's say, a fermion and a scalar particle, right? Then what will be the spin for that of that composite function? That composite function we are doing. So it's a matter of just adding that of the spin of this and that of the spin of that, and then you get the spin of that particle we are talking about. I hope it's clear. Okay. I have to emphasize that they said explain elementary particles, state the types of elementary particles based on spin. I know this is not something I have to waste time on. We can move on. But please pay attention to the objectives over here. Make sure you be able to solve them. It's not nothing new, it's what you've done. So we move on to what quarks are, because we said quarks are what makes up the basic, that are the elementary particles for protons and neutrons. For now, or as it stands, because any further analysis has not done for us to know that maybe that's not the basics. Okay. So the standard model, the particle physicists now believe they can describe the behavior of all known subatomic particles within a single theoretical framework called the standard model, incorporating quarks and leptons and their interactions through the strong, weak, and electromagnetic forces. And I know we've done this already. The force that exists between nuclear particles, that's the strong force, the weak force, and the electromagnetic forces. Okay. And these are the forces that exist between the quarks and leptons. Gravity is the one force not described by a standard model. The standard model is the fruit of many years of international effort through experiments, theoretical ideas, and discussions. We can summarize it this way. All of the known matter in the universe today is made up of quarks and leptons, held together by fundamental forces, which are represented by the exchange of particles known as gauge bosons. So basically, everything in this universe is made up of the quarks and leptons, right? And these particles are held together by the fundamental forces, either the strong force, the weak force, or the electromagnetic force, right? And the exchange particles within themselves. And this is known as the Gauge bosons. Okay. One guiding principle that led to the current ideas about the nature of elementary particles was the concept of symmetry. Nature points the way to many of its underlying principles through the existence of various symmetries. Now I move on to the quarks itself. Most of the standard model is just trying to explain the basic or the made up of every particle in the universe. Okay, which is just talking about everything is made up of the leptons and the quarks. Where the leptons are the makeup of the protons and neutrons, and the leptons are makeup of the electrons and the neutrinos. And these are the things that come together to make an atom. Okay, and every particle, the smallest particle, the smallest part of any particle we think we know was the atom. So if these are made up of the atom, then it means every object is made up based on these things. And that's the basic. And the forces that exist between these leptons and quarks and how they interact with each other is what we say they are the bosons, Gauge bosons. Okay. Now we are going to the quarks, and the quarks is what we are saying is the basic or the makeup of the protons and neutrons. So what are then quarks? And is there any way we can further break down into another simplest form, or is there a way of calling some of these quarks? And that's what we are going to look over here. Most of the matter we see around us is made up from protons and neutrons, yes, which we all know, which are composed of up and down quarks. So they are saying everything that we are seeing around us, most of the matter we are seeing around us is made up of protons and neutrons, of which me and you know is true. But we are saying these protons and neutrons, which are the quarks, are made up of up and down quarks, meaning that the quarks, we have what we call up and we have what we call down. Okay, means when you take quarks, first we have a quark we call up, and we also have a quark we call down. Okay, so realize up and down. So this is the opposite of this, or this and this antimatter, as we always say, that the universe, everything else is antimatter. So if you have up and you have down, you should know that obviously this is the opposite for that. So you have up and down, which is one part of the quarks. The present standard model, there are 6 flavors of quarks. So if you are talking about the present standard model, we say we are having 6 flavors of quarks. And if you talk about the flavors, we are just talking about these quarks, how we will be able to call them, or how they are being called, okay, or the name assigned to them. And that's what we are talking about. They can successfully account for all known mesons and baryons. That's if you are talking about the mesons and baryons, which are about 200, they are all made up, or they all account by the presence of these 6 flavors that we are talking about, and these flavors are the quarks. Okay, quarks are observed to occur only in combinations of 2 quarks and 3 baryons. So if we talk about quarks, they exist in 2, and we talk about if we talk about mesons, it's a combination of 2 quarks, and if we talk about baryons, they're a combination of 3 quarks. Okay, so for example, if we take a proton and we say the proton is made up of 2 quarks, then that proton is said to be what? A meson. But if you take a quark and it's made up of 3 quarks, then we are saying that composite is known to be what? Baryons. Please. Is it clear? Have I been able to explain that to you?
So please come again.
I said, assuming if we take I'm coming. That's a minute, sorry. Okay, so we said if you take any composite particle, right, and that composite particle is made up of two barons, I'm sorry, two quarks. It's made up of two quarks. Then we are saying that quark is called, or that composite particle is called a meson. And if you take a baryon, or if you take a composite function, it's made up of three quarks, that means that composite is called a baryon. So for example, assuming we have, let's say, assuming you have a composite matter, right? And it's given by up plus up plus down. Right. This composite function is said to be what? A baryon. Right? Why baryon? Because this composite function made up of three quarks. So 1, 2, 3. You get it? But if you take a composite function and it's made up of just two quarks. So for example, we have up plus up. Just two. Then we said this composite is known to be meson. Is it clear?
Okay, sir. What are up plus down? Is this still meson?
Yes, it's still a meson.
Okay, thank you.
So far as it's a quark. So we have some of the particles or the composites that is made up of a quark and a lepton. Okay. So if you have a quark and a lepton, just know the number of quarks in there. And if you're able to identify the number of quarks in there and it's 2, then that thing you are dealing with is a meson. But if you identify the number of quarks in there and there are 3, then you are doing a baryon. So irrespective of it being 2 quarks with, let's say, 3 leptons or 3 leptons, it's still a meson. Why? Because you're having 2 quarks in there.
Okay, sir. Thank you.
All right.
So please, I need some clarification.
Okay.
We said most particles are composite particles, and then so far the real 2 elementary ones are the leptons and then the quarks.
Yes.
So why is it that when we are doing this movement, we don't compare the quarks and the leptons? I are comparing quarks and mesons. I don't know if you get my question. Because I was thinking that it should be, this is the quark, from quark, they move on to the lepton, so that we can say that since they are currently the elementary, or what is regarded as elementary particle, then the comparison of the ups and downs should be between the 2 and not a different.
We are dealing with the quarks separately because for the leptons, right, they are just the composites for just electrons and the neutrinos. Okay. And we know if we talk about these electrons and the neutrinos, those are the ones responsible for reactions, for example, conducting and all those kind of things, right? But then those that are able to generate energy, right? Generate energy or undergo certain changes, whether being radioactivity or anything, are the protons and the neutrons. Okay, so we want to see what is made up of those things that makes
follow
it.
Up. So, a follow up, please. What is the basic difference now between the quarks and the mesons? Since we know that of the quarks and the leptons, that this one. So to understand it better, it means that the positron and then the electrons, they don't radiate energy. So now what's the difference between the quarks and then the mesons? So that I can now link the two. Thank you.
So meson is a quark. Meson and baryons are all quarks. But then you see, quarks is the basic things, right? If you talk about quark, they are the basic ones that make up the protons and neutrons in the atom, right? But if you are saying meson, it means we are talking about a combination of two quarks. And if you are talking about baryon, you are talking about a combination of three quarks. Mr. George, is it clear?
Please, not really clear.
So it's like let's take the class, right? And we are saying the class here, we are quarks. Okay, we are quarks. But for us to be a meson, then let's say it's me and you, we are two. So we being quarks and we are combined together to form one particle. Then we are saying we are meson. Why? Because even though we are quark, but then we are just two, we are two combination of quarks. So when we add us up, we become a meson. Likewise, if you take me, you, and Castro, and we add us up, then we are saying we are meson. Baryon. Why? Because even though we are quarks, we are made up of three quarks.
So I think this is an example like in biology, when we are studying the cells, we say that a group of cells will make up a tissue. So tissues are still cells, but they come together to form what we call a tissue. So that's the same thing with the quarks and the mesons and the baryons. When two quarks come together, we call it a meson. They are still quark, but since they are together, we don't call it a quark now, but we call it a meson. And when three also comes together, we call that one also a baryon. Although they are quarks, but since they are now together, we can't call it as a quark, but we call it as a baryon. So I think that is the explanation.
Thank you, Mr. Castro. Mr. Joy, is it okay now?
Yes, sir.
So for example, we can say the cell
Please,
that I'm coming. The cell that Mr. Castro is talking about is the quarks, right? So if you talk about a tissue is just a meson. And now if you talk about an organ, which organ is the third step? We can talk about a baryon. Yes.
Yeah. Francis, I think the answer about
my question has to be, is that they are composites, so it could be up or down, right?
Yes.
So it doesn't matter whether it's up or down, but if it is down, you have two downs, that means it's still a meson.
Yes, it's still a meson. It's still a
And
meson.
if you have three downs, it's still a baryon, right?
Yes.
Okay. But you made a mention something about the electrons. You get electrons, even if it's three, I want to get that part clear.
We've not gotten to that part yet, so let's treat the quarks first. Because the electrons is basically about the electrons and the neutrinos. So we want to finish with the quarks, which is the protons and neutrons, before you go to that side.
Okay, thank you, sir.
All right. Mr. George, is it clear now?
Yes, it's okay. Okay, thank you.
All right. So that is that. In the standard model, okay, we've talked about this already. Quarks are observed to occur only in combinations of 2 quarks and 3 baryons. So as we said, in other words, quarks come in 6 varieties, but physicists usually talk about them in terms of the 3 pairs. So the flavors or the pairs, that's what we are talking about. And we have up, down, and you realize anytime you take one, the opposite of it is also there. So we are talking about the thing itself and its antimatter. We talk about the thing itself and its antimatter. So we talk about up and talk about it down. So ideally, the 3 pairs, they are basically just 3, but their pairs are what is making it the 6. So we have up and down, we have charm and strange, and then we have top and bottom. And these are the basic quarks. Okay. And the up is represented by U, down is represented by D. The charm is represented by C, and strange is represented by S, top by T, and bottom by B. I hope you are okay. So even as we have this, we also have their, you don't let me confuse you for now. Quarks also have antimatter counterparts called the antiquarks. So in as much as we have in these quarks, we also have their antiquarks. Okay. Where are we? Okay. Designated by a line over the letter B. So example, if you want to find the antiquark of up, right? So we know quark of up is equal, is equal to U, right? So antiquark of up is written as this. Okay, so anytime you see any symbol with a dashed line on top of it, trying to indicate, let's say, a vector, then we are dealing with the antiquark of whatever we are dealing with. I hope it's clear. Okay. Protons and neutrons, particles that form the nuclei of atoms, are examples of baryons. So if you take a protons and neutrons, we say they are examples of baryons. Why? Because they are made up of more than 2 quarks. So the number of quarks in the protons and neutrons are 3. They are more than 2. So they are 3. But they said the examples of baryons, and baryons are made up of 3 quarks. Okay. Positive and negative karyons are example of mesons. Now, if we are talking about mesons, we can talk of positive and negative karyons. Okay. And karyons is just a small k, with positive here will be the positive karyon, and k with negative here will be a negative karyon. Okay. And if you are talking about mesons, mesons are what we say they are made up of 2 quarks. So if you are talking about this, they are all mesons. Okay. Is there any question? Okay.
Good.
Hello, sir.
Okay.
Good.
Hello, sir.
Yeah, please, I'm listening.
The previous slide, we were talking about 2 quarks making a meson.
Yes.
And when it comes down there too, we have another combination that will also give us another mesons.
Which one? This one.
Yeah, so quark also have antimatter counterpart called antiquarks, designated by a line over the letter symbol. Quarks combine to form heavy particle called baryons, and quarks and antiquarks combine to form mesons. Is it different between these mesons and the one up there?
No, it's not different. We said quarks is a combination of, meson is a combination of two or more, two quarks, right?
Yes.
I hope that point is established. That one you understand. You understand, right? Mr. Bernard. Mr. Bernard, are you here?
So I want to clarify something.
The network is breaking.
Hello there.
Yeah, I can hear you now. I can hear you.
Okay. Okay. We are saying if you talk about meson, it's a combination of two quarks, right?
Yes.
And now we are saying if you have a combination of a quark and its antimatter, it's also a meson. Why? Assuming if you have U plus U bar, these are all quarks, right?
Okay.
And this is a quark, this is a quark, and these are two. So this is also known as a meson. Is it clear?
Okay, so the
combination is not about maybe just the matter alone, but if you have a matter and its antimatter, summing up to be two, it's also a meson.
Okay.
Yes.
Because I was thinking that the anti will be like opposite to the main one,
so that it cancel out.
Yeah.
That's where I think you spoke about annihilation, pair production and pair annihilation. Maybe after this you can relate it to that. That's why I explained the pair production and pair annihilation, which I know is in modern atomic physics as well. So even if I don't know if there's a session that will try to relate them, then fine. If there's no session, after the course, you should be able to relate them based on the understanding, based on this one, and what you also understand at that place.
Okay.
Yes. Mr. George, are you having a question? Mr. Francis, please go on.
Yeah, I want to clarify this thing. Is a quarks are observed to occur only in two combinations? That's a meson, right?
Please, I can't hear you well.
Is a quarks combined?
Yes.
When two quarks come together, they form a meson.
Yes.
Yeah, so it's a quarks combined to form a heavier particle called a baryon. But I thought the baryons are rather three quarks, right? So I don't know, I'm getting confused.
Why?
It's the same thing, no.
It's the same thing.
Same thing. They are saying
Because
that
when they
quarks
spoke
combine.
about it, we specify the number of quarks.
Say, come again.
I said it's the same thing because they didn't specify the number of quarks they are talking about. If they were saying quarks combined to form, let's say two quarks combined to form a heavier particle, and they say it's, it's a baryon, that's where there will be a question mark. But now they didn't specify the number of quarks in there. Okay.
Okay. So it's the same thing.
Yes, it's the same thing.
Okay.
All right. Any other question? Okay. Quarks have the usual characteristics of having a fractional electric charge, unlike proton and electron, which have integer charges of +1 and -1, respectively. Quarks also carry another type of charge called scalar charge, which we'll discuss later. Then go to some properties of quarks. So the properties of the various types of quarks have been summarized in this table. So we have up, down, charm string, top and bottom. And now we have U. Please, they're supposed to be small letters, not capital, so take notes. a small U, small D, small C, small S, small T, and small B. And now their spin is always half. Their spin, they are all having a half spin number. And then we also have their charge. We also have their charge and their baryon number. And we have their mass. That's their rest mass, okay? Their mass, their range. But please, don't chew this table. I'm not going to ask you from this table that I'll give you the thing I need. So don't worry yourself by chewing this. If you chew it, how will brain? Okay, so don't try to memorize it or chew it. Just it's just for you to know. Okay, it's not for you to chew. Okay. The masses should not be taken too seriously because the confinement of quarks implies that we cannot isolate them to measure their masses in a direct way. The masses must be implied indirectly from scattering experiments. These masses represent a strong departure from earlier approaches which treated the masses from the up and down as about 1 out of 3 the mass of a proton. Since in the quark model, the proton has 3 quarks. The masses quoted are model dependent, and the mass of the bottom quark is quoted for 2 different models. But in other combinations, they contribute different masses. So as I said, please don't chew it, because even as much as we have this masses, it's not even a fixed or it's not constant, right? It varies. That's why I said don't chew this. If I'm asking you to find anything of this sort, I'll give you everything you need. And I don't think I'll even worry with that kind of thing. Okay. Where are we? In the pion, an up and an anti-down quark field a particle of only 139.6 mega electron volt of mass energy. While in the row vector meson, the same combination of quark has a mass of this. So they are talking about a pion, right, which is made up of an up and anti-down, right? And they said the energy is 139.6 mega electron volt of mass energy. While rho, which is a vector meson, right? And that one is also made up of just 2 quarks, because the third meson are made up of 2 quarks. And now the pion we have here is also a meson. Why? Because having 2 quarks, which is up and down. But if you look at the rest mass energy, you realize they differ. One is 139.6, whilst the other is 770 mega electron volts. So they always differ. Okay. Each of the 6 flavors of quarks can have 3 different colors. The quark forces are attractive only in colorless combinations of 3 quarks, that's the baryons, and quark anti-quark pairs and baryons. So as you know, if you take quark and anti-quarks, they have a color code for that, which is the meson. And we talk about the baryons, which is made up of combination of 3 quarks. They also have their own characteristics as far as the color is concerned. And possibly larger combinations, such as spent quarks, that could also meet the colorless combination. Quarks undergo transformation by exchange of W bosons, and those transformations determine the rate and nature of the decay of hadrons by the weak interaction. Okay. Now go to what we call the up and down quark, the up and down quarks. The up and down quarks are the most common and least massive quarks, being the constituents of protons and neutrons as an ordinary matter. So if you take any proton, this is the makeup of it. So you have 2 up and 1 down. So it means a proton is what? A baryon. Because it's made up of 3 quarks, and the quarks are what? Up and down. Madam Felicia. Madam Felicia. She is not here. Intira, Kasami, Kwakata Sementia said that. Okay.
Yes, it's our yes and two. Our yes and two. Our only ladies doing physics.
Now Madam is it Belinda or Benedicta? She's also
So,
here.
yes, there are three. There are three people. Three yes and two in our midst. All physics. Only
Really?
three. Yeah, only three
Then I
women.
know of just two, only Madam Felicia and Madam, is it Belinda or Benedicta?
Hey, Benedicta and Jemima. Hey, my yes and two at my
Jemima,
center.
share.
Jemima.
Jemima,
Yeah.
me ono nkasa o.
Yes, hey.
Nkasa o platform
Yes
bi
and
pa.
Papa. Oh, share.
Oh, I
Easy.
see. That class, I'm one underground artist. Yo. Almost for
That's all.
Okay. So now, if you want to find the combination, you realize we have 2 up and 1 down. So it's if you are comparing the up, it's 2 out of 3. That's the probability. Okay, and that's why we have it this way. Now, if you are talking about the down combination, it's 1 to 3. I hope you understand it. So, for example, if
No,
you don't understand it,
no, please come up again.
okay. Now we said the proton is made up of 2 up and 1 down, right? And basically it's a bion because it's made up of 3 quarks. Okay. Now, assuming if you are asked to find the probability of bions, up in the proton, how do you find it? Or assuming you have semi probability problem starts.
No, sir.
And then
I
you
have
do
not
this
done.
in math.
Oh, yeah,
I
yeah,
said,
yeah.
is it
But
the
not
basic
as
one?
part,
And also the basic one we do it.
not as part of our program, but we have done it before. But not as
Okay.
part of our program.
Okay. So assuming if you take this and want to find the probability of up in this bion. Now, what is the total quarks made up of this? It's 3. 1, 2, 3. Right? And how many ups do you have? You have 1, 2. So what is the probability of up in this proton or in this bion? So
To be 2
the
out
up,
of 3.
yes, and that's what we have over here. Likewise, if you are to find that of the down, so we have 1 out of 3.
Yeah,
What is
1
clear?
out of 3.
And that's what we are talking about. I hope it's clear.
Yes, sir.
Yes, sir.
Okay. Now, the fact that free neutron decays, the fact that free neutron decays. So we realize when we are talking about how do you call it? Radioactivity, right? We said if the neutrons is greater than or equal to 20, that will undergo radioactivity, right? Why? Because the nucleus become unstable. Okay, and hence the nucleus starts, the neutron starts splitting itself. I hope you've not forgotten that if the number of neutrons is more than the number of protons, it has to disintegrate so that the atom becomes stable. And by doing that, that's where we get the radiation and radioactivity. I hope you've not forgotten.
Yes, sir.
Yes, sir.
Okay, so assume you have an excess neutron and it's undergoing radioactivity. At the end of the day, it has to decay from neutron to a proton, so that the proton that we get will be quite approaching to the number of the neutrons, and then the atom will be stable. Agreed? Do you
Yes, sir.
agree? Okay. And the process they undergo is what you have over here. We've done this before, but I know some people will say they don't understand. And this is just a neutron undergoing decay. We are not doing anything as far as the up and downs or the quarks are concerned. We are just trying to show the decay process for this kind of atoms. Okay. So we are not doing anything. And now the nuclear decay by beta decay process, like now a beta decay, some of the process they undergo is this. Okay. Now let's try to chip in the idea of quarks, right? Now we know the neutrons and the protons are not the fundamentals, but they are made up of the up and downs. Okay. Now it's thought to be the result of more fundamental quark process giving us. Now we have a down, we have an up, we have an electron, and we have the energy that is being released. Okay. Okay. And sometimes this energy is what we are saying. They are sometimes neutrinos. They are sometimes neutrinos. Okay. So likewise, the same way this undergo decay. Assuming if you are having a proton, right, which we say is made up of this, and now it's not making up of 2 up and let's say 2D and 1U. How do this undergo disintegration for it to be a stable baryon? And those are some of also the particles of the combination or the activity they also undergo. Okay. Now we move on to the strange quark. And the strange quark, we said we have charm and strange, right? And now we are going to the strange. In 1947, during a study of cosmic ray interactions, a product of a proton collision with a nucleus was found to live for a much longer time than expected, which is 10⁻⁻10 seconds instead of 10⁻⁻23 seconds. So ideally, the nucleus, if they undergo collision, they undergo it with a certain a certain range of time, which is assumed to be 10⁻⁻23 seconds, right? But then there was an experiment or there was an observation that a proton undergo a collision with a nucleus, and now the time that it was expected to live, which was 10⁻⁻23, it was much longer than that. Okay, and then what could have been the results, or what could have fueled that? To say maybe if I'm able to spend from, let's say, from nature, I'm able to spend, let's say, 10 cedis in 3 days, right? And this time around, I had 10 cedis, and instead of 3 days, I exceeded it to 5 days. It will be a question mark because the normal may have to spend the 10 days in 3 days. Why am I spending 5 days? What prompted that? Okay. And that's what brought about what they discovered for it to be what we know as a strange. This particle was named the lambda particle, and the property which causes it to live so long, and that strangeness. And the name starts to be the name of the one of the quarks from which the lambda particle is constructed. So the reason or the rationale behind why I was not, or I exceeded that limit to 5 days, okay, is what was discovered to be the strangeness, because it's strange that instead of 3 days, now I exceeded to 5 days. So what made it? So assuming when I was doing the 10 cities, I was having extra, let's say 2 cities somewhere. Now that 2 cities somewhere that they were able to discover that I have some 2 cities somewhere, they named that 2 cities strange. Instead of saying 2 cities, they say no, because we don't know what that was. They are calling it strangeness. And that's what brought about that strange name for quark. I hope it's understood. The lambda is a baryon which is made up of 3 quarks. Now the lambda we are talking about is made up of 3 quarks. So the lambda is a baryon. The lambda is a baryon. Okay. And the combination is a down, an up, a down, and a strange quark. Okay, so the lambda, which resulted in that it's made up of up plus down plus strange. Okay. The shorter lifetime of 10 to negative 23 seconds was expected because the lambda as a baryon participates in the strong interaction, and that usually leads to very short lifetime. The long observed lifetime helped develop a new conservation for such decays called the conservation of strangeness. So because of that strange delay or that span of time, lead to another conservation, which you know the conservation of strangeness. The presence of a strange quark in a particle is denoted by a quantum number S, which is equal to -1. The particle decayed by the strong or electromagnetic interactions preserve the strangeness quantum number. The decay process of the lambda particle must violate that rule since there is no lighter particle which contains a strange quark. So the strange quark must be transformed to another quark in the process. Now that can only occur by the weak interaction, and that leads to a much longer lifetime. The decay processes have shown that strangeness is not conserved. Now, if you take the lambda, right, as we said, it's made up of, it's a baryon, so it's made up of 3 quarks, which is up, down, and strange, right? And this is made up of a proton and a pion, negative pion. Okay. And this is also, we have about, how should I say it? We don't really have a specific combination for the strange. So they were trying to do try and error to see what could have been the lambda, because the lambda was the one responsible for that delay, and they are trying to find out the fundamental of that. So they first come out with the up, down as a pion, and they also came up with the neutron and the pion zero. And why did they come by the proton and neutron? Because we said when you are talking about baryons, right? The basic ones we know for as a building block is a proton and neutron, and these are the ones that is found in the nucleus of the atom. So if something of that has occurred, then means it will be either the proton that is causing that or the neutron that is causing that. So we first find the baryon and the combination for that of the proton, then you do that for the neutron. But in the case of doing that, you also have to make sure that at the end of the day, everything will be balanced. Everything will be balanced. Okay. The quark transformations necessary to accomplish this decay process can be visualized with the help of the Fermion diagrams. The Fermion diagrams. Okay. We'll go to stranger. The up and down quarks are sufficient to describe the proton, neutron, pions, and delta baryons. However, the story does not stop there. Other particles are also created in strong interactions. That particles which did not fit into the 2-quark Weber model and were called strange particles. Bubble chamber experiments were used to examine the properties of beings of strange particles and demonstrated that the strange particles could travel microscopic distances before decaying. Because you know, when you are talking about these forces that exist between the nucleus, they are they can't travel faster, right? And the distances are very short. And the distance is what we say there is a Fermi meters, which is 10 to the negative 15 centimeters. Okay. But now we realize it was in the macroscopic distances. And when you talk about macroscopic distances, we are talking about a very long distances, which is quite strange. Okay. Their stability could be explained if there was a new, almost conserved quantum number associated with these strange particles. This strangest quantum number is conserved in strong interaction. In order to decay, the particles have to undergo a weak interaction, which changes the strangeness. For example, some strong interactions produce charged carrying particles as K plus or minus with masses just less than 500 mega electron volts, and which carry the strange quantum number which is the P plus P, that's proton plus proton, which yields proton plus proton plus the current positive and current negative, of which you know the current positive and current negative will go annihilation. And then they will get what we also have there already as the proton there. Okay. Then move on to the charm quark. In 1974, a meson called the JGSI particle was discovered with a mass of 3,100 milli-electron volts, over 3 times that of a proton.
Hello, sir.
Yes.
Sir, please, so at this stage, do we have 3 different quarks, or one quark exhibiting, showing itself as a charm and then the strange, or there are 3 different ones in all?
I don't understand.
I said that we have the quark, another type, another strain of quark called the strange, another strain of it called the charmed, or it is one, it is the
yeah, it's a
quark,
basic quark that we know that we are talking about.
No, yes. So I'm saying that the quark that we are talking of, there are 2, right? One is charm and one is strange, or there are 3 in actual fact, and then one of them is strange, one of them is the charm, and then the other is normal quark.
I think this one, I think in the model it was stated that quarks are known in different ways. We have the up and down, the strange and charm, and I think he mentioned another one of it too. So those are the ones that we are now talking about. We have already done the up and down. So now you're looking at the charm and strange.
Okay, so it means that if we are considering all of them, we have the up, the down, the strange, and the charm, right?
And top and bottom.
Yeah, and top and bottom. That's the last one.
Okay.
I think it's okay now, sir.
Okay. I think it's even time for break. Should we go for the break or we should continue?
The break is very necessary.
Okay, then let's go for the break.
My colleagues.
But then with this, I didn't really bother you with this as far as your destiny is concerned. But then with the objectives, yes, you have to solve them and understand them. I just want us to go to the complex one so that we can well, you don't worry, you do it.
Oh, no, if you want us to go with, maybe you can sacrifice it so that maybe we'll close it.
Oh, not closing per se. I mean, these are all readings. They are not something that really requires explanations, right? But then I was going through to see if there are some things that we need to really sit down, because as far as your exam is concerned, I'm not sure we are going to worry you with some of these things so that you could read it on your own. But then I know my people, if I say read it on your own and you are asked somebody, you say you've never seen it before. So I'm also
how many this is the masters no be say o.
Ma ka ana Ibrahim abeka no obeka se no mawi ubeka. You don't, at least we will go through them, but then maybe we won't spend much time, because I was thinking there are any and probably I'll get you guys tutorial questions that will really tackle the ones that you have no idea of. For the meantime, so that when they come back from the break, instead of doing the same thing, we can do the EM field theory for the extra tour. Said the baby to me share yet me on how far we can go, because this is the last week, right? And you have to finish the EM field tour as well. So what do you guys think? Should I let you guys, should we switch to the EM field so that when I get to the tutorials, then
so let's switch.
I think it's a laudable idea.
We think what you think. So let's switch. The only
Mr. Ben, I don't see that. Mr. Ibrahim, hold on.
Yes, switching call EMF.
Mr. Ibrahim, what's the case?
me say, we think what you think. So if you think your thinking is better for us,
Mr. Castro. Mr. Castro also say.
We think alike. We think alike.
yeah, look at Frank.
media, maybe na me call shopping to me the main prof on a kind of meeting. And almost we think like you, Diana, we think like you now. We think you're thinking.
Yo, can you offer why? All right, then let's go for the break. When we come, we just switch to the earphone and we move
Okay,
on.
sir. Okay, sir.
Sir, when are you coming back?
Oh, probably maybe in the next 15 minutes or so. So let's say by 9:20, we all should be here. Too short, ma'am. I don't know me, I'm here. Maybe I'll just walk around for a while, but then if you guys are, when you come, then we start. So you used to give me the time. What time should we resume?
9:20, 9:29.
The 9:20 is okay, sir.
All right, then let's go for the break and get back around
George,
9:20.
George, go and watch you. Go and watch.
As usual, as usual.
Georgido.
Hello.
Hi.
Hi. Hi, sir.
Are we back or we are not back?
We are back.
We are back, sir.
Oh, okay. Please, I guess you can see my screen now, right?
Yeah.
Okay. So, uh, this was where we got to the last time, and I think we solved it. So we move on to current density. Didn't we do current density?
I think we got to this place. We did this one.
We did the current density here.
Yes, please.
Okay, so we move on to conductors. Conductors, and basically conductors, it's not something really new that we don't know. Conductor is simply just any material that allow the flow of electrons. Okay, that allows electrons to move through them. And we can talk of examples as metals. And with the metals, we have each and their resistivity and their conductivity. Okay, so in as much as it's even a metal, it has a rate at which it makes electrons move through them. Okay, so that is also that. Is there something here I need to know? Move to capacitance and dielectric materials. Okay, this is as you say, so it's for so you can start with the unit 3. But then this is not something you should stress yourself on, because I know you've done this in electricity and magnetism. That if you want to find the capacitance, capacitance is just the relation of the charge and the voltage across it, and you can talk of types which you have the parallel plate capacitor. You should also know when you are talking about capacitors in series and in parallel, how are the arrangements and how do you find the equivalent capacitance, whether in series or in parallel? Okay. And as, basically the energy stored in a capacitor, and those the basic things that we all know. That's what this one is talking about. So it's not anything above what you did in second year. That's electricity and magnetism. It's not above that, it's just the same thing. So I won't stress you that, even though you are the one to read it. I'm just trying to let you know the basic things.
Embody.
So we move on to we move on to
Ebeba kwana ko ready. Say yonko
it's having that's why. So basically the unit 3 is talking about some of the laws that make up, or the laws that this electricity and magnetism obeys. Because he spoke about the fact that electricity and magnetism are always moving hand in hand. They are perpendicular to each other when it comes to the field. And that's how come you have electromagnetic field. Okay. So in as much as we are talking about a field, that's the area under study, and its electromagnetic field means it's having both the properties of electricity and the properties of magnetism as well. But what are some of the laws that govern any matter or any particle or any conductor that find itself in this kind of force? And these are the laws that this session talks about. So the first one, and these are the laws that also makes up the Maxwell's equations. So the Maxwell's equation, you can talk of the first one, which is the Gauss law. Then can talk about the Gauss law in E field and Gauss law in magnetic field. Yeah. Can talk of the Biot-Savart's law and all that. Okay, so if you talk Biot-Savart's law, what does it say? So it states that the magnetic field intensity, okay, the magnetic field intensity produced at a point P by the differential current given in that's the IDR, is proportional to the product of the current and the sine of the angle between the element and the joint P. So and the line joining P to the element, and it's inversely proportional to the square of distance between P and the element. And that is given as that. And where is the diagram? This is the diagram. So assuming you're having a conductor, right? Let's say this is a conductor. So Madam Fisher, Madam Benedicta. Okay. So assuming this is our conductor, right? Assuming this is our conductor, and the conductor is having a certain current through them. And let's say the current through this conductor is I. Okay. Now at this point, okay, assume the current at just this point is called, let's say, DI. Why DI? Because we are talking about the current just at this region only, right? We want to find the impact of the magnetic field acting on the current at this point. Okay, making a certain angle to that of the field, and the angle is say alpha. How do we find that? And that's all what the Biot-Savart law talks about. And he said it's given by IDI, that's the total current through the conductor, times that of the small portion we are dealing with, sine the angle that the conductor is making to the field, divided by the distance, that's from this point to the field, squared. Okay, so it's more or less like the inverse square law. So the DH, let me change the color. The H is basically equal to, now the current we are finding it over here, current I, which is the total current through this conductor, times now the current that is having the impact of the magnetic field alone at this point, which is what? Labeled as the DI. Okay. And sine the angle the current meets with the field. Because this is the electric field. Because the current is passing through and the electricity is passing through the conductor. That's the current. And that becomes our electric field. And now this is the magnetic field. So the angle the magnetic field is making with the electric field. But mind you, we say always they are what? Perpendicular to each other. So assuming if they didn't state the angle, then means obviously the angle between them will be 90. And when it's 90, means the whole thing will be zero. There will be no impact of the field on that, because sine 90 is what? 0. Sorry. Then the impact will be just perpendicular to it. Okay. But now, assuming the angle is not 90, then what will be the impact? Meaning when it's 90, the impact of the magnetic field will be that greater than that of where there is no angle. Okay. So if the angle here was supposed to be 90, then means the current or the magnetic field will have a much impact on that of the current. But if it's less than 90, then means the impact of the electric field will be less as compared to that of the magnetic field. Mr. George, is there any question? Okay. So if the angle here is 90, probably the impact of this will be much higher on the field. But if the angle is not 90, then the H will be lesser compared to the R. Okay. So that is that for that. And also, what you also need to take into consideration is the distance between where the magnetic field is and where the current is. Okay, because if the current, the distance increases, okay, the impact decreases. But if this one increases, the one also what? Decreases. Please, I hope you guys are here. And answer me, you're muted. Can you hear me?
Yeah,
Yes,
we
sir.
can hear
Yeah,
you.
Okay.
Yeah.
Yes.
So, Madam Benedict, are you calling me?
No.
So I'm back first lesson. I feel now over.
I was around from the beginning.
Hey, madam.
Oh, truly. I was
Okay.
around before you were saying that Felicia and the rest.
Oh, okay.
Mm.
All right. So as I said, the distance also very important. So with this one, the most things that we pay attention to is the angle the field makes with the conductor, and also the distance from the magnetic field to that of the electric field. That's the conductor. Those are the things that really affect the thing. The magnitude of the current and the distance, the small changes we are looking for, even though it matters, but then it doesn't really influence the whole thing as compared to the distance and the angle. So if the angle is 90, obviously it's going to be much greater, right? Because everything here will be 1. But if it's less than 90, then it means you are going to get 0 point something. And it means when you multiply this, it's going to decrease. Okay. Likewise, the distance also plays an important role. If it's closer to it, the impact will be higher as compared to if the distance is further. Okay. And that's what the Savas law talks about. And the Savas law can also, we can also treat it in the, okay, basically we treated everything in just the normal thing that we know from the electricity and magnetics. But as I said, if you are dealing with electromagnetic field theory, you have to also factor into consideration the kind of plane you are dealing with, or the kind of Cartesian geographical plane you are dealing with, whether a Cartesian, spherical, or whatever. But then when you are dealing with this, we have to also take into consideration the unit vector of the distance from the conductor to that of the E field. So for example, if you are dealing with this, where's the diagram? If you are dealing with this, now our R is from this point to this point. Okay, so our unit position unit vector will be our A of R. Okay, where our R will be defined, that may be from this point to that point, so that you can find the magnitude of that and get it. So when you get that, you can divide it by the vector by the magnitude, then you get your unit vector R, AR. Because when you are dealing with it, as far as there is a distance C, you have to factor out the unit vector for the distance or the position vector. And that's why even as much we had this as the law, that's when you're treating electricity magnetism. Just get to this point and you're ending over there. But with this, you go further and then you talk about the direction. Okay. And mind you, you realize when we were treating cross products, I don't know whether it was electricity and magnetism or whatever. And we said when you cross two vectors, the resulting vector is the vector which is what? Perpendicular to the two vectors, right? Do you remember that?
Yes, sir.
Okay. And we went ahead and say if you cross two vectors, let's say A cross B, we can go ahead and simplify this, and it gives us the magnitude of A times the magnitude of B, then sine theta. I hope you've not forgotten this.
Yes, sir.
Okay, and we also talk about the dot product that we said is the same thing, but this time around is what? Cos theta. Yes.
Cos theta.
So all what I want to draw your attention to is that when you have a cross product, right, and you want to eliminate the cross, you can eliminate the cross by just multiplying everything and then introducing a sign. I hope you understand what I'm saying.
Yes, please.
But the sign will take away the cross. Likewise, if you have a sign and want to eliminate it, you can take away the sign, then you cross the two vectors that we have. I hope you understand what I'm saying.
Yes, please.
Okay. In that case, this is our Besava's law, right? Now we want to factor in the unit direction and also eliminate the sign factor over here. Okay, so now we are assuming, or the assumption is that now the magnetic field is perpendicular to the electric field, and hence the E or the alpha is 90 degrees. Now
Sir.
that assumption.
Hello, sir.
Yes.
Please, how has it become necessary for us to introduce the constant 1/4 pi?
Because here it was just the relation between them, right? We are trying to relate, the Besava's law was relating the magnetic field to a current conductor in a region where it has an influence of magnetic field. We want to know at the end how is the field or how is the current affected by the magnetic field. Okay. So we just find the relation, but to find the relation, we have to find a way by eliminating the relation and putting it in that you equate them to see the quantity of whatever we are looking for. Okay. But then as far as we are treating electricity and magnetism, always the constant of proportionality is what you know as the K. And the K is what you know as 1/4 pi epsilon naught.
Okay, all right. That's okay. Thank you.
All right, you're welcome. So as I said, the assumption is that now the angle between them is 90 degrees. Okay, now if the angle between them is 90 degrees, then means we can cross the I, right, with a certain vector. And now what vector are we dealing with? The unit vector between the direction. Please, are you with me or you are confused?
We are with you.
Okay. So that at the end of the day, we know when we're doing the Coulomb's law, we said F is equal to K Q1 Q2 all over R, let me put it this way, R Q all times R1, sorry, R2 minus R1. That is its F on 2. I hope you've not forgotten this expression. Where we said if you find the magnitude of this, then it can cancel one of the QBA so that then they have K, Q1, Q2 all over R squared. I hope you've not forgotten. Okay, so the same thing applies here. Realize here it was to the denominator was R squared. And hence, if you substitute the unit vector there, we are going to get the R squared can now be written as the vector R divided by the magnitude R or Q. Is this correct? This is magnitude, so that, I'm sorry, the vector. So that if you find the magnitude of it, you can cancel all of this.
Yeah,
This is
correct.
correct. Okay. If that's the case, then means the R squared over here, right? We can place it with this whole thing. So that our GH will be giving us I di sine alpha over 4 pi not alpha R cubed. Then this times our vector R. And this agreed.
Yes, sir.
Okay. If this is true, and we are saying now the field is, we are assuming the field, that's the E field and the I field are perpendicular to each other, and hence it's 90 degrees. And if we want to eliminate the sign from it, we can just bring the cross product. Then means our DH can now be written as, now we have our I, and now this is a vector quantity. Why a vector quantity? Because the current is moving through a certain conductor, but at this point it's having a certain region, or it's in a space. So it means you can find the position vector at which you are looking for the current. Okay, so that becomes a vector quantity. So if the vector quantity, it means you can cross this with the vector direction R. Okay, then at the end of the day, we just divide the whole thing by the 4 pi, then our R cube. Is it correct? Hello?
Yes, sir.
Are you guys with
Find alpha and the R before
Should we move on or you are confused?
Sir, come over again.
You
Come
said?
over again, sir. Do go over it
Can
again.
you go through?
Because I'm a bit
Yes,
confused
please.
here.
Okay.
Yeah,
We are
go over a
saying
little bit again.
according to Sabat, he is trying to relate the current, right? The current passing through a conductor, a certain conductor, placed in a region of magnetic field. Okay, and we are trying to find the relation between the magnetic field and the electric field. Okay, and that is what is illustrated in this diagram. That assuming this is the magnetic field, and now this is the current conductor. Now, I want to find the current, right, at exactly this point. Okay, the impact the current exactly at this point have on the relation with that to that of the magnetic field at this point, which is separated by a distance c r, right? And the current running through the whole conductor is known as our I. And the current is also making an angle, say alpha, to the magnetic field at the certain portion that we want to find the influence. Okay. And we said it's related as the H, which is the magnetic field, is also proportional to the I sine alpha over R squared. Okay. We made mention that if you want to eliminate the constant of proportionality, if you want to eliminate the proportionality sign, then it means you have to introduce the constant of proportionality, which is the K. Okay. And the K we already know in electricity and magnetism, which is 1/4 pi epsilon naught. So we can eliminate that and then you substitute, instead of bringing the proportionality sign, you substitute in the K. Okay. Now, after getting the K, we also know that the current the length we are doing here is from this portion to this portion. So it's just not in one dimension that as we used to know. As we say, it's only in the S coordinate or in the Y coordinate or something. It's in the it's diagonal, right? So it means at the end of the day, we have to find the position vector for the R. So getting the distance for the R in the position vector form, then you find the unit vector for the R. Because realize when we are treating stuff like this in the electromagnetic field, you have to figure out or you have to factor in the unit vector component of each thing that you are dealing with. Okay. And we are saying the unit vector component for the position vector R is known as AR. So that the R squared times everything here times AR, where the AR will tell us the exact point that the field that this DH was situated in the field. Okay. Now, we also say that the unit vector AR is always given by the vector R divided by the magnitude of the vector R. I hope you've not forgotten this.
No, please.
No, sir.
Okay. So in this case, as we saw earlier from the Coulomb's law, it means when you have this whole expression, that's this whole thing, it can be written as the H is given as I, the I sine alpha all over. Now, from the, let's say, Coulomb's law, as I said, you can just rewrite this as R cubed. Then you multiply this by the vector R. Okay, so that if you find the magnitude of this vector R, it can cancel one of the exponents here, then it get back to this whole thing. Agreed?
Sure, say.
Okay. Because this vector R is in terms of I, J, and K. So when you solve it, it will give the exact position where the DH is. Okay. Now, establishing this, we know now this point, that's the current conductor here, right? This current passing through this I. Even though it's a scalar quantity, but then the point at which we want to find the changes, that's just this DI, is also a vector component. Why? Because this point is given by a certain coordinates. I hope you understand it. Because this is just passing through, but where we want to find the difference is a certain point within the Cartesian plane. So it means we can find the coordinate or the position for the DI. Agreed. Please do you agree with me?
Yes, sir.
Yes, sir.
Okay, if you agree with me on that, then means this our DI here is also a vector quantity. Okay, so it means you're having a vector quantity of the DI and also the R. Okay, which are all vectors. But then you and I also establish something that when we are dealing with cross products, or when you have say A cross B, okay, vector A cross B, and you go ahead and you expand this, it's going to give you the magnitude of vector A times the magnitude of vector B, or sine theta. Okay, where theta is the angle between A and B. Agreed. So if that is the case, and we say we have this whole thing as the angle between the current and then the distance to the magnetic field, then we can eliminate the sine theta, then just substitute in the cross product so that our DH can be written as I DI. Then instead of sine theta, we bring our cross products. Then our R here is the position vector specifying where the magnetic field is. Then we divide the whole thing by the magnitude of the distance, all Q. Is this true?
Yes, sir.
So that is what we were trying to establish. And now, as I said, the R here is a vector quantity. So even if you do it at the end of the day, it will give you the exact position where the H is. And that's all what they did over here. They didn't do any strange thing there. Agreed. Mr. Castro, is it clear now?
Actually, I got a question. I left the list. I think it's not you are particularly on the side. I think I'm getting it with what you are taking on the side. I think
Castro, I can't hear you.
Thanks. I'm saying that I got a call. So I looked at the explanation. With what you are taking now, I think I'm getting the idea now. I think I'm getting the idea now.
Okay, okay. All right. So that is all what they were trying to establish over here. So basically, the Biot-Savart's law is trying to relate the current conductor at a certain point, which has an impact or which have an influence of a certain magnetic field on the charge. Okay, and that's all what Gustavat's law talk about. And that brings us to the right hand rule. The right hand rule. I hope you've heard of the right hand rule before. I'm not the first person to tell you this. That's if you have a certain current, right? I'm sorry, if you have a conductor carrying current and it's applied in an electric field, how do the field evolve around the conductor? Okay. And that's all what it talks about. And this also relates the velocity, the electricity, and the magnetism to it, of which when we are treating a velocity selector, we talk about the E field, the B field, and the velocity. Okay, the velocity. So that's all what it talks about. Then we can also...
Sorry.
Yes.
So if you look at the two diagrams, the previous slide, no, please, where the term rule is, so they name one as, yeah, this particular one, yes. Yes, okay. This one. They name the first one as a right hand rule, and then the second one was right hand screw rule. Are they the same, please?
Yeah, they are the same. It's the same principle.
Oh, okay.
They are the same principle. The only instances where there are changes is when you see, when you are dealing with a magnetic field, it has poles, right, south and north. So when they are pointing either inside or outward, that's only when the direction changes.
Okay.
Yes, that I think it's even stated. Yes. Okay. Where the field is pointing is what only changes the direction. Apart from that, everything just maps the same thing.
Okay. All right.
Okay. Then we can talk of this is just what you did is just a current carry conductor, right? So you can also talk about the Gustav's law in terms of a certain surface. Okay, and we can talk about it in terms of volume as well. So when we are talking about the line elements, that's where you know our DL, which is giving us our DXI plus DYJ plus our DZK. Okay. Now when we are talking about the surface, okay, the surface, the S, that's where we need to pay attention. Now talking about surface, the surface, is this in terms of Cartesian coordinate system, cylindrical or spherical? I hope you understand what I'm trying to say. With the DL, it's always the same, whether it's in cylindrical, Cartesian, or spherical. While the surface and the volume, it differs when you are dealing with either a Cartesian, either a spherical, or either the cylindrical. So pay attention. But then it's the same principle we applied, the same or the same law. To realize this is the final expression. Okay. But if you are talking about in terms of volume or volume or surface area, the same thing, just that you now have to factorize the plane we are dealing with. The plane, whether a Cartesian, cylindrical, or spherical, and that's all what changes the whole thing. So if you are talking about line, as we saw earlier on, it's given by this. Okay. It's given by this. And if you are talking about surface, it's also giving us this. And mind you, you see they are doing it in terms of Cartesian. So you see you have your AR. Just that when you are doing the current, the I in the surface area is KDS, where the K talks about the surface area and the S, sorry, the K talks about the current passing through that surface area, and then the S is the area we are taking our attention to, or the area under consideration. And when it comes to the volume, is JdV, where the J is the entire volume that we are dealing with, and the JdV or the dV is a small volume within that entire thing that our attention at. Okay, that's the volume under study, and that's the dV. Okay. And the current for the volume is also JdV. So if you come here, you realize it's just the I that keep on changing. So that when you are talking about a surface area, instead of IDI, it's now KDS. And for volume, instead of IDI, is JdV. I hope it's clear.
Yes, sir.
Okay. Now I have a certain example. Say applying question. Please.
I said,
Yeah.
yeah, if can go over this side.
Okay.
It seems I'm getting lost, Kakra. So if you can recap the
From
equation
here
from
or
seven.
from where? Okay. Now, if able to establish that.
It's 1.7. How did we arrive at that?
Okay, if able to arrive establish that our DH is given by this. Okay, where the DH is the differential current, differential flow that you are dealing with, and the DI is the differential current. Okay, now assuming we want to find the field, but this time around, just not a small field that is having impact by the entire field. Okay, means we will integrate the whole thing here and we integrate the whole thing here so that whatever I get will be H instead of the H. Okay, and that's what is being done here. Okay, that's what is being done here. But mind you, when we are dealing with the line that's the A. Okay, that is what we explain over here. Okay, that's what we've done over here. And you are saying, okay, fine. What if now we are not dealing about it in terms of line, but this time around we are talking about it in terms of a certain surface. Okay, so that now this DI is not a DI anymore, but it's given by this. So we have the entire surface here as K. Okay, we have the entire surface as K. Now, what is the current, right? Passing through this small K. This small K, that this small surface within the entire K surface, the impact the field will have on it. So that this time around, instead of the IDI, okay, instead of the IDI, which is from here to here, it's no more IDI, but what is KDS. Because the K is talking about the current for the entire field, and the DS is talking about the small field that we are paying attention to. Okay, so instead of our normal expression, which we know our DH is equal to I DI cross R over 4 pi R cube, right? Now this IDI is just meant for the current. Now we are looking for that of the key, the surface area. So instead of IDI, it's no more RDI, but rather it's KDS, so that our DH be giving us KDS cross R over sorry, 4 pi R cube. Okay, So that this time around, if we want to find the entire age that is affecting this whole thing, we just integrate the age, then we integrate the whole thing over here. So that this integration will cancel the D here, and then we have only age. Okay, and age will be giving us the integral of K R, sorry, K R cross our DS all over 4 pi RQ. Okay, and now we are integrating over a certain surface S, which is this one. So we have to put the limit over here, which is along this surface. So assuming the coordinates of the surface were given, that's where you substitute them inside. I hope it's clear. Likewise, if you are doing for the volume, the same thing, instead of IDI, it's no more IDI, but what GDV. So the whole thing is, instead of our IDI, you just substitute the GDV in there, then you have our R cross dV over 4 pi RQ. Then you bring your volume over here. So that when you are doing the volume, now you have to go about a triple integration because the volume have both 3 coordinates. So assuming if you are dealing with a spherical coordinate system, it means you
I read I got a call.
I believe say Yusuf is having a network challenge.
Okay, okay. I got a call, so I just had. All right, thank you.
hello.
Hi, sir.
Yes, sir.
Hey, I didn't know my line was off, so I can say um Mr. Francis, or who was asking for the clarification. Hello.
We can hear you.
It's,
We can hear you.
Is it clear now?
Yes, sir.
With the explanation to these three, is it clear now?
Yes, please. But the thing is, can we be asked to prove the formulas?
No, 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 no.
Okay,
Why would I stress you with that?
okay.
Yeah. So that is that. Now, it's some of we have, for example, they said apply question 1.6 to determine the field due to a straight current conductor. of final length AB as in figure 1.5. Now they said this current is carrying, sorry, this filament is carrying a current in the Z direction, right? And they want us to find A to B. Okay, but the point of interest is this. This is our R. Okay, so it means now our limit is what? From A to B. But the angle the A is making and the angles B are making has also be into consideration. And that's all what we deal with. So that one is also solved over here, which I won't really bother you with it, because if I want us to go through this, it will take us 3 days. To take us more than 3 days.
24 hours, 3 days.
Because you say people are telling me this
24 hours, 24 hours, and 1 3 days, and I'm sleep.
Because you guys told me 1 year differentiation, 1 year integration, or maths. So if I want us to go into the integral aspect of all this, I'm wasting my energy. Won't say. But then what you need to know is how to apply this law to whether it's a Cartesian, a cylindrical, or spherical, and also whether it's a line filament, a surface, or a volume. Okay. So we can move on to so this guy is talking about the Gustavus law. Yeah, hello. Hello.
Sir, continue, please.
Oh, okay. I thought someone was calling me. So
Continue, sir. Continue.
Okay, so this point is just talking about the Gustavus law. Then we go on to the Ampere's law. The Ampere's law. Okay. So the Gustavus law, we realize we are finding the magnetic field, right? Now the Ampere's law, we are also finding the currents. The currents. And mind you, the Gustavus law, we were talking about it in terms of line, surface, and volume. But the Gustavus law, we are talking, the Ampere's law, we are talking about it in terms of an enclosed surface. An enclosed surface. So it states that the line integral of tangential component of the magnetic field strength around the closed path is equal to the current enclosed by the path. The line integral of the tangential component of the magnetic field strength around a closed path is equal to the current enclosed by the path. And that is what is stated over here. Okay. So if you find the magnetic field enclosed within a certain field, right, the current enclosed by that field is directly proportional to whatever is within that enclosed surface. And that's all what Ampere's law is also talk about. And Ampere's law is also quite similar to Gauss' law, right? Because when you are dealing with Gauss' law, you talk about the flux that is contained within a certain enclosed surface, which is proportional to the current that is leaving that enclosed surface. But this time around, we are not dealing with it in terms of flux, but rather we are dealing with it in terms of magnetic field, the magnetic field strength, and then the current that is found within that surface, right? The differential current. Okay. Okay, at first glance, one would think that the law is used to determine the current I by an integration. Instead, the current is usually known, and the law provides a method of finding H. So ideally, you realize, or when you look at this, because everything is equating to the I, you think we are now looking for the current, but I did in the actual science is the H that we want to find, the magnetic field strength. Just as the Biot-Savart's law stated, but with the Biot-Savart law, that one it just gives you the relation between the field and then the current with a certain distance from the field. But this one we are talking about a closed loop. So it means when you're talking about Biot-Savart's law, we are talking about it in terms of free space, a field, right? A field which is not enclosed. Okay, where you have the currents and the magnetic field having impact on each other. And when you're talking about the Ampere's law, you are talking about the same relation, but this time around in an enclosed surface, which tells us that within this surface, at any point, the current is the same. Yeah, at any point, the current is the same. Likewise, at any point, the field applied is proportional to the magnetic field applied is proportional to any point that we select. Okay. Okay. This is quite similar to the use of Gauss law to find D, given the charge distribution. In order to utilize Ampere's law to find H, there must be a considerable degree of symmetry in the problem. Two conditions must be met. One, at each point of the closed path, H is either tangential or normal to the path. And B, H has the same value at all points of the path where H is tangential. So as I said, at all points, the magnetic field is the same since we are dealing with it in terms of a closed loop. Okay, but always the H must be tangential to the path. It must be tangential to the path. Okay. Now they say use Ampere's law to obtain H to an infinitely long straight filament of current I. And that's it. Now everything is stated here, right? Everything is stated here. And with the question they said infinite long straight line filament H. Okay. To obtain a due to infinitely long straight filament of current I. Now, if you are talking about infinite filament of this one, say R, then means at the end of the day, you are looking for, definitely you talk about a conductor which is carrying the current, right? And all conductors is typically wires, okay, has a cross-sectional area of what? What is the area of any spherical object or any how should I put it? Yes, of any circle.
Pi r square.
Area
of any.
No, I mean the surface, the total angle.
The total surface area.
Yes. No, the filament, if the circumference, let me put it that way. Because the current is passing the circumference.
It's pi r square.
Huh?
Oh, it's 2 pi r.
2 pi r.
It's 2 pi r.
Is the area which is pi r square. Sure.
180 pi r square.
I thought you were asking for the area.
We are talking about the circumference of the wire, because that's where the current is. You see, if you take the entire wire, right, the filament or the magnetic field is having impact on the filament, and these filaments have the same current distributed alongside each part of the current conductor current conductor. Okay, so at each point, yes, at each point have the same current. Okay, so if you have the entire circumference, it means you can find the field that is being applied at each point. Okay, and then you just substitute the entire circumference in this whole thing. That's when you integrate it over the closed surface. Okay, so that it will be If you integrate the entire closed surface, you get it to be 2 pi r. So that you have our 2 pi to be the same as the current, which is enclosed within that circumference that we are dealing with. Okay. But at the end of the day, we are looking for the magnetic field. That's the magnetic strength H. So you make H the subject. Making H the subject, we get 1 out of 2 pi. Get 1 out of 2 pi, and that will be the magnetic strength for the current carrying conductor at each point. Okay. Then can go on to applications of Ampere's law. Applications of Ampere's law. We now apply Ampere's circuit law to determine H for some symmetrical current distributions, as we did for Gauss' law. We will consider infinite line currents, an infinite current sheet, and infinitely long quasar transmission.
Upina de dene koso na minimze wa ya ntina na mi frɛ no.
Okay. So let's take a look at the infinite line charge. Okay. So you are just applying this law to an infinite long charge. They also apply it to infinite current sheets, and then an infinitely long quasar transmission line. It's just the same thing that we apply, just that this time around we are dealing with the current in terms of a line, right? You have the current, and then it is in a circular form. Then we have it also in terms of a sheet, okay, a sheet, and we also have it in terms of infinitely transmission, quasar transmission. Okay, and this is also being done there, which I won't really bother with that one. So we move on to magnetic flux density.
Mr. Yusuf, because we master's level, omo yes course we are advanced electromagnetic field.
Yes.
I didn't theory.
That's the way basics.
That's a detail.
You hasn't you.
Masters no be, don't be afraid. You can do it.
That one day you do it. Not that you can do it, you will do it. It's a must. It's a must. But then it also depends. You see, the masters, when you are doing the first year, you have 4 compulsory courses, and you have 3 other courses which you are mandatory to select at least one, so that you make up with your credit hours. So you have to select the other 3. But then, unfortunately for you, this course is the advanced is a compulsory or a core course, so you can't skip it. Mr. Ibrahim, I didn't know, sir. And one no more to, because course we are 1 and 2, right?
Of course, I mean, yeah, me who's to park, see, na down or channel.
This Maxwell equation thing, when we're doing the thermal physics, we didn't really cover it too. Tiama, we are totally
The
confused.
Maxwell's equation under thermal physics is different from the one here.
Oh, okay.
Yeah, the Maxwell's equations under thermal physics has to do with the state equations. Okay, but this one we are trying to relate the Gauss law, the Ampere's law, the Biot-Savart's law we are trying to relate them, and that brings us about the four Maxwell's equations. And ideally, this course is into two sessions. You have EM field theory 1 and EM field theory 2. This is just the one. If you have done the two, maybe when you are doing the masters, that will be very easy for you. But then, one need to know the end of the book. Okay.
So is it a build up on electricity and magnetism that we did?
The EM field theory 2.
Yes.
It's a build up on this one.
Yeah, okay.
Yeah.
All right.
So magnetic flux density and mass.
Hello, sir.
Yes.
Hello, sir.
Yes.
Hello, sir. Doc.
Yes, please. I'm listening.
Please, it seems I don't have a soft copy of this. I'll be glad if you can push it on our platform.
Castro. I think Castro. Okay.
We have the song. We have it too.
Mr. Francis, almost more because I remember I gave it out. Okay.
I've gone through all the files. I'm not seeing it.
Okay, don't worry. Probably I'll reshare it or something with Castro. Then maybe we'll share it to you guys.
Thank you, sir.
So we are just talking about magnetic flux over here. And remember when we are dealing with electric flux, we said electric flux is related to electric field density is related to electromagnetic field strength as E. Excuse me. The electric flux density D is equal to epsilon naught E, where we said the epsilon naught defines the field we are dealing with. Likewise, the same to the magnetic flux density, the same thing. So this is also related to the magnetic flux density is related to the magnetic field with a quantity of mu naught, where the mu naught is the constant of what? Permeability of free space. Permeability of free space. Where that of the epsilon naught was permittivity. E naught is permittivity, M naught is permeability. So note that they are different. Okay. And there's nothing much here to do. I think what I need to really pay attention to is the Maxwell's equations, which is my interest that you need to know for now. But yes. So let's look at the Maxwell's equations. I didn't skip it because it's not important to. I skip it because it's the same thing for the electric flux density. Okay. The same thing we did for the electric flux density is the same thing for magnetic flux density. The only difference is instead of epsilon naught, now it's mu naught. Apart from that, everything there is the same. So please read through. This is what my interest is, because this is where, yes, please question Mr. Bernard. Hey, sorry, Mr. Samuel, please go ahead, your question.
Yes. So if you question us on these ones, will it be like you did with the thermal?
You said?
I'm saying if you are going to question us on this, will it be like you did with the thermal physics?
How was the tema?
If you ask us to write short notes.
Oh no. Please, no. Now, even if I ask you to write the short notes, I don't mean notes. I mean some key parameters. With this, I can just ask you to state the Maxwell's equations, right? Either in the differential form or the integral form, and that's all. I won't go ahead to write no. And I even doubt if I don't know. Let's see. Okay. So the Maxwell equations for static EM fluids are given in this table. And basically, these are the four Maxwell's equations. The four Maxwell's equations. And we have it in the differential form. We have it in the integral form. And these are the applications. So if you take the first one, it's the Gauss law for electric field. Gauss law for electric field. And we all know. And the second one is also the same as the Gauss law, but this one for the magnetic field or the non-existence of magnetic monopole. That we said when you have a certain surface, right, where magnetic is being felt, immediately you leave that surface, you don't have any part of the magnet on you or the magnetic influence on you. Okay, and that tells us about the monopole of magnetic existence. It's the same as the Gauss law for magnetic field. And the third one also talks about the conservativeness of electrostatic field. Okay, the conservativeness of electric field or the electrostatic field. And you also have the fourth one, which is the Ampere's law. The Ampere's law. So these are just the four laws. These are the four laws that you need to know. With this, they are always so simple to quote. These two, they are always so simple to quote. Okay. That's del dot B is always equal to 0, and del cross E is also equal to 0. Okay. And this also talks about, so in most cases, someone can choose to write the first, or someone can choose to write this. The person is not wrong. Someone can also choose to write E A cos theta is equal to Q over epsilon naught. That's also not wrong. In as much as you could code the Gauss law, I'll give you your marks. Okay, in as much you could code your Gauss law, I'll give you your marks. Okay, so the first two talks about the dot product, and the last two talks about the cross product. And the last two talks about the cross product. And these are the four Maxwell's equations that you should know. With this one, you should know. It should be at your fingertips. These are also okay. And now the last two is also always talking about a line integral. Whilst the first two is always also talking about a surface integral. Where the first two is always also talking about a surface integral. And these are the four Maxwell's equations you should know. So maybe knowing this, then you can call it a day. We meet on tomorrow Then we continue the magnetic skill and vector potential invasion of the surface and adverse law and forces due to magnetic fields. Okay.
Okay, sir.
All right, sir.
Question.
All right. Thank you very much, sir.
Mr. Castro, and walk or hold on, Mr. Samuel, your hand was higher too.
Yes, sir. I wanted to ask if tomorrow we are continuing with. I didn't hear what you said. Whether we are continuing with this or we do the normal particle physics out. Okay. This is particle. Whether we will be doing the EM.
Yeah, we'll be doing the EM. The particle we are done.
Oh, okay.
Yes.
Since this is our last meeting, I'm asking you, can we maybe? No. I mean this weekend. After that, I think on Monday or so we have one more meeting. So I'm asking if maybe we can have
a meeting with you guys on Wednesday, tomorrow and Wednesday.
Yes.
Okay, it's Wednesday rather, not Monday.
Yeah.
Yes, I was asking if maybe we can have some meeting where we can, let's say, do some brush up for the examination. Maybe we can, if that would be possible. Where we can. So you see, where we can, let's say, do a little brush up and focus on one or two things, if it is possible.
I think with Dr. Charles is the one in charge of nuclear and particle physics. And yesterday he spoke to me that I should get to tutorial questions. So basically, I'll go through some of the tutorial questions.
I wrote to them.
You spoke to him, right, Castro?
Yes.
Yes, for him. Yeah. For Dr. Charles, you don't have anything to really worry about that because for him, he's not that difficult. He's not difficult. So whenever we do such a thing, he always wants the best for him. So you just make me do something for him like that. So there's Dr. Peter, who is sometimes some way he doesn't really buy into that idea. Okay. So with the NPP, don't worry, I'll get to tutorial questions for you to try your hands on. Let's see the
okay, sir.
Yeah.
All right, thank you, sir.
You're welcome. Mr. Castro, after the meeting, if you are free, you can call me, okay?
Okay, I'll do that.
All right.
Definitely do that. All right, thank you, sir.
Castro, please call him. Make sure you call him, please, be back.
And now, Mr. Francis, call me now.
And brothers, please, our discussion. Let's keep meeting so that we can be solving some of these questions. It will help us, please. Those who are not part of the group, we in our Momra, so that we'll be solving these questions. It's very important.
And then you can any part 20 and on my joining.
Mr. Castro.
The thing is, Mr. Francis, Mr. Francis, what is your interest? Anyway, we meet tomorrow.
Mr. Castro.
Okay, please, members, the first thing to make us immediately after this question, and say that
We can't hear you.
Somewhere to go. We can
Your
hear
line is
you.
very bad.
We can't hear you. You're hang up. I'm working. So you can hear
please mute
Can't hear you, boss.
We can't hear you. We can't hear you.
Can you hear me now?
Yes, it is better
Hello?
now.
Can you hear me now? All right. I'm
Yes,
saying
it is
that
better.
Festus want to meet us immediately after we're done with our lesson because he has some place to go, something to do. So he would like to meet us earlier than planned so that he'll be able to go. So let's just meet him on maybe 10:50. Let's just use some few minutes to freshen up. Then 10:50, we meet him. I'm going to call him that Yusuf is done, so he can then start the lesson. Okay, so please, Bear with
Hello.
him for us. Okay, I'm begging you. Yes.
Please, some of us we would have to charge our phone. So
Then okay, then please can we make it 11 o'clock?
The thing is that you wanted us when you called me during the class. You thought us a Yusuf was done. So even you wanted us to start around that 10 when you called. And
Okay.
I think that he might not be able to meet us till maybe I don't know the time that you have to go. I don't
Oh,
know the time that you have to go. So please let's just
all right.
accommodate him for our own sake, okay?
All right. We will.
Because
We
we
will.
have a lot.
Then please, let's make sure that is being recorded, so that in case some of us miss because of the battery system, we can get it. Because if they don't record it, we'll be in trouble.
Okay. I'll insist. Okay.
So
All right.
Castro, the
So
link. Are you going to post the link or you are using this link?
yes. I'm going to post the normal link that we use. The normal link that we use.
Oh, okay. Then
This is
let's join.
we haven't
Kindly
continued
repost it.
so I'll do that. Don't worry. Okay.
Thank you, sir. So let's meet.
All right then. Have a wonderful day to you all. Let's meet at the first class. Bye bye.